This is tutorial 1, question 4. And in this question we have a tank with a pipe coming out of it, and that pipe splits into two, and the water exits the end of the pipes into the atmosphere. So in this problem we have to consider the velocity head of the fluid that's leaving the pipes. So the pipe information is given: friction factors, the lengths, diameters, and also the heights. The first pipe is 23 meters below the level of the reservoir, and the second pipe is 30 meters exiting below the level of the reservoir. Alright, so to calculate the losses in the pipes, we once again use the Darcy formula, and in this case we're going to use the original version. Head loss due to friction is FLV squared over 2GD. So that's the velocity version of the Darcy formula. So the head loss due to friction in pipe number 1, 0.04 times 60 meters V1 squared divided by 2 times 9.81, the diameter 0.1, and that gives us 1.223 V1 squared. Head loss due to friction in pipe 2 is 0.032 times 18 meters V2 squared divided by 2 times 9.81 times the diameter 0.05 gives us 0.587 V2 squared, and the head loss due to friction in pipe 3, 0.032 times 36 meters long V3 squared divided by 2 times 9.81 and the diameter 0.075, and that is 0.7828 V3 squared. Right, now we apply Bernoulli from A to B, and B is the exit of the first pipe. So if we write out the full Bernoulli equation, it will look something like this. ZA, which is a static height, plus PA over rho G, which is a pressure term, plus VA squared over 2G, velocity term, is equal to ZB plus PB over rho G plus HF1 plus HF2 plus V2 squared over 2G. So that's the full Bernoulli equation. Substituting, we get 23 meters is equal to V2 squared over 2G plus 1,223 V1 squared plus 0.5871 V2 squared. We can then put that in terms of V2, and that will be the square root of 23 minus 1, 2 to 3 V1 squared, and we divide that by 0.638, and that can be equation 1. Now we need to apply Bernoulli from A to C. Then we get 30 is the height difference, V3 squared over 2G plus head loss to friction pipe 1 plus head loss friction in pipe 3. So 30 equals V3 squared over 2 times 9,81 plus 1,223 V1 squared plus 0.7828 V3 squared. And that can be simplified. Alright, let's just undo that. We can say V3 is then equal to the square root of 30 minus 1,223 V1 squared. That's divided by 0.8337. And that would be equation number 2. And for continuity of flow, Q1 equals Q2 plus Q3. So therefore D1 squared, D squared V1 is equal to D2 squared V2 plus D3 squared V3. So all we've done is we've substituted Q for VA, and because the diameter is the only variable, we can delete the pi over 4. So substituting, we have 0,1 squared V1 is equal to 0,05 squared V2 plus 0,075 squared V3. So we've just made an equation in terms of velocities instead of discharges. V1 is equal to 0,25 V2 plus 0.5625 V3. All right. from equation 1 and 2, we can substitute for V2 and V3. So therefore, V1 is equal to 0.25 times the square root of 23 minus 1,223 V1 squared, and we divide that by 0.638 plus 0.5625 times the square root of 30 minus 1,223 V1 squared divided by 0.8337. By successive approximation, or using your calculator, we can determine the value of V1 from that quadratic equation. So therefore, V1 is equal to 3,395 meters per second. So if we want to take that back to discharge, Q1 A1 V1 pi over 4 times 0,1 squared times 3,395. So that gives us a value for Q1 of 0,0226 meters per second. But they've asked us to calculate and give the answer in liters per second. So therefore Q1 is equal to 26,664 liters per second. And substituting in equation number 1, we get V2 is equal to 3,736 meters per second, and Q2 equals 7,3356 liters per second. Substituting in 2, V3 is equal to 4,369 meters per second, and Q3 is equal to 19,328 liters per second. And as you can see, this problem can be worked out in terms of velocities as well. And that's the end of the problem.